designing a PKI. In this nugget, we're talking about designing a PKI, or public key infrastructure. In order to design a public key infrastructure, you have to answer a lot of questions that we'll be taking a look at down through this. So, for example, the first thing you'd want to know is, why do we even need a PKI? What are its purposes going to be? You have to understand those things and what you're going to use it for in order to get at the root of why you want to build your PKI. And then you also have to have some understanding of encryption and signing, and I'll do a couple of quick demonstrations there for you of those things, so you can kind of see PKI in action, or at least a little bit. And we're going to use self-signed certificates in the first example, but at least it shows you how a certificate is used. And then we'll take a look at templates as well. There are 3 different versions of templates available, and we'll see what the requirements are for using each one of those. We'll also take a look at who or what needs certificates. I mean, if you have thousands of users that need to have user certificates, your PKI infrastructure is going to look dramatically different than if you only have a group of developers and there's only 12 developers that need certificates. So it's going to be dramatically different depending on who or what needs them. And then you also have to take a look at the security requirements. There's a number of different ways to make certificates more secure, but it's not always better to make them more secure and to use longer key lengths or more complex algorithms. Sometimes it's better to use weaker. Okay, we'll take a look at the reasons why. Also, the business requirements. Do you have any customers or clients that may be government contracts, for example? If you do, they may have requirements for your certificates that you need to comply with in order to keep your contract. We'll also take a look at Active Directory and the role it plays in designing your PKI, and the biggest part of that will be with what we call enterprise certificate authorities. One of the first things you want to determine when it comes to planning your PKI infrastructure is you have to determine why you even need a PKI. If you can establish why you need a PKI, this will go a long way to determining how you configure the rest of your infrastructure. Everything from the kind of cryptography that you decide to use to the number of servers you decide to implement and so forth. And here's just a small start as to why we might need a PKI. And these are questions that I don't have answers to. These are just questions that we have to think about when we try to determine if we want or need a PKI. One of the primary purposes, of course, of a PKI is to sign something. If we sign something, this confirms that it did come from us, and it also provides something called non-repudiation, where I can't deny that I signed it, because only I have my private key, which is used to sign, so therefore it had to have come from me. It couldn't have come from somebody else, and so far, it's even impossible to forge that or to fake that. So, very little chance of me denying that I signed something once I've done that. And then, there's also the purpose of encryption. Encryption can be in a lot of different things. You can encrypt a file. You can encrypt an email. You can encrypt some kind of some message traffic. All those kinds of things are possibilities with a PKI. And of course, public key infrastructure is not the only way to do this. You don't have to do it using only certificates. In the past, we've used symmetric keys, and I'm going back 30 years or so. But in 1976, some guys by the name of Diffie and Hellman came up with a method for using public and private key methods to be able to sign and or encrypt data. And that sure makes things an awful lot easier. Let's also take a look at an example. This doesn't always guarantee that you're going to have airtight security in every respect. This is still going to depend upon the user factor. And I'm going to quickly take a tangent here, just briefly, to show you something that I think might be of interest to you. Here is something that my wife received. My wife received this email saying that our online banking had been blocked. Great Scott! This was an emergency because it could just possibly be that the debit card would not work now and she couldn't go shopping. So what does she do? She sends me a text. She's only upstairs in our house, and I can actually hear her clicking away on her phone sending me this text. And she sends this text and says, "Hey, what's our online username and password? Because I have to do something there." And I said, well, okay, she's entitled to know. So I just started to text her back. Of course, I could have just about whispered it, and she could have heard me. She's right upstairs. Anyway, then it occurred to me, why does she need to know this? So I went upstairs and I asked her, and she said, well, I got this email saying that our online banking had been blocked. So of course I clicked where it told me to click, and when she did that, it took. And this, by the way, is a very believable email, I guess, to the casual user. And my wife's not technical, by the way. But anyway, she went to this web page when she clicked on that item, and boy, doesn't this look authentic! And of course, it says the name of my bank over here, and it says the location. Everything here is almost exactly the way it appears on the actual web page. But the key thing here that almost made me really wonder if I shouldn't go through with this is right here, HTTPS. Wow. What do we tell our users? Anytime you see HTTPS, that means it's encrypted, and certificates have been used to confirm the identity of this party. And also we see this padlock over here, so you know you're being safe when you go to one of these websites. Well, obviously these people had gotten a hold of a certificate, and by the way, I did investigate this, but I have committed to not naming the entities involved. But there's a well-known certificate authority public identity out there on the internet, and if I name them, you know who they were that issued the certificate that authenticated this web page. If I did a little other investigating, by the way, I would see that this wasn't really bankofamerica.com. This is really, whatever this is over here. That's the actual site that we are connecting to. Anyway, I point all that out to say it still depends upon human factors in certain places, but it would still go a long ways if we can have a good PKI infrastructure that issues certificates that can really button down security pretty well. But despite that exception that I just showed you, for general purposes, normally when you have certificates which are issued by a trusted root authority, a trusted certification authority, then you can normally trust the signatures and the encryption that they provide. Now, here's a few different applications for certificates out of a PKI. And when I say applications, I don't mean executables or something or programs. I mean just different ways of using it. One of the ways you can use it is in a network. You can use it for 802.1x authentication. This is where we can confirm that the parties involved on the network are really truly who they say they are. And if you don't have certificates that can authenticate who you are, then you will not be able to even get on the network or to use any of its resources. Same kind of a thing with a VPN. You might have level 2 tunneling protocol or L2TP or something like this, where you can use this in your VPN, and again, this can be used to increase the strength of user authentication if you're using L2TP with IPsec encryption. And then with IPsec itself, with this, notice that certificates aren't going to actually play a part in the encryption and signing of the IPsec protected data. There are other methods that are used for that, but they definitely will authenticate the two endpoints in the transaction, so at least we can be sure that the server we think we are communicating with truly is the server that we are supposed to be communicating with. So that's, again, another use for certificates. Now, keep in mind, though, that if you're in an Active Directory environment, and that's often the case in corporations, then Kerberos is going to be used instead of certificates to provide that authentication. And then there are other methods involved in IPsec to encrypt the data if you want to do that as well. Also, with a certificate issued from a PKI, you can use signatures. A signature would confirm that this email that I send, for example, really did come from me, and it cannot be forged or faked or anything like that. So it confirms that it came from me. You can also use it to in implementing code signing, so that we can confirm that any programs we write or drivers my company makes really did come from us, and we sign them with our certificate so that we can confirm that as well. And then we can also use them for encryption. A number of different ways that this can take place, among which is things such as EFS, or the encrypting file system, which has been available since Windows Server 2000. And of course, you don't have to have a certificate to be able to encrypt a file. You could use a self-signed certificate that's not issued by a PKI. So I guess you actually still need a certificate, but it doesn't have to be issued by a PKI. Let me show you what I mean here. I'm just going to go ahead and minimize some stuff right here, and then I'm going to open up Windows Explorer. Here we're just going to go to my local hard drive, and I've got a temp folder here. I'm just going to create a document here. How about that? We'll go to create a text document, and I'll just call this encrypt me self-signed. Okay, I don't have a PKI infrastructure right now at all, so I don't have any way of issuing certificates from a certificate authority. And if I go to my search console here, which I custom created, and you can do that by choosing File and Add Remove Snap In from a blank MMC console, notice that for the current user there are no personal certificates right now. But if I right-click on this document and choose Properties in Advanced, then notice that I can encrypt the contents to secure the data. This means then that only I, and I'm just going to encrypt the file here, only I will be able to read this document now and be able to open it. Notice that it changes to a green color to indicate that it is encrypted. And if I double click on this, I can enter in data and save it, and we're fine with this. Okay, I can open it up as many times as I want, and it's really pretty much transparent when I do that. Now let's go back to my Search Console, and if I refresh the screen here, we'll see that when I encrypted that document, it generated what we call a self-signed certificate. So if I go to double-click on it and then go down here to look at it, it says it allows the data on the disk to be encrypted. That's what I used it for. And the certification path does not point to a CA. It points to my own account here, so it's a self-signed certificate. Now let's take a look at what happens here. I'm going to go ahead and right-click on this and choose Delete, and then the certificate's actually still stored in memory. So what I'm going to do is I'm going to actually log off, and when I log back on again, we'll see if we can still open up this document. Okay, so then here I've logged back on again. Let's go back to that same location here. Remember, I encrypted this document, and then I deleted the certificate that I used to encrypt it in the first place. So now when I try to open it, oops, access denied. You know what? I don't care what's in this. This could be confidential company information. We don't have a backup for, vital data. We will never get this document back. There's no possible way. Even if I were to right-click here and choose another document that I wanted to encrypt, maybe I want to encrypt this one now, it won't make any difference because it's going to generate a new self-signed certificate with new keys, and I still won't be able to open up this one. Okay, access is still denied, but this one I can open now. Why? Because they were both encrypted with different sets of keys. And I'll never get this one back. Those are just some eggs that I will never be able to unscramble, so to speak. I can delete it, though, of course, so I can do that. Now, here's the thing when we come back to a PKI. This was a self-signed certificate that I used to encrypt these documents, but boy, wouldn't it be better if I had a public key infrastructure, such that when it created a certificate and issued it to a user, that it could also store a copy in Active Directory. And that way, if we did lose the key for some reason that it encrypted that document, we could then unencrypt it by recovering that certificate. Or use something called a data recovery agent, or a DRA, that would be able to do that. And then besides encryption, you can also use certificates for signing. So with this, I would have a message right here. This could be a driver, this could be a file, this could be an email message. And what we'll do with that is the cryptographic function will run a hash function, or a complex mathematical calculation against this original message. Then it will result in a mathematical result over here called the message digest. Then we take the signer's private key, we run it against the message digest, and the result is an encrypted version of this message digest known as the signature function. And that will result in our actual digital signature here. Now note that in this whole first part of the process, I use my own certificate, and within my certificate there is a private key. And I use my private key to do this signature and create a digital signature. The recipient of my email message, they will receive the email message, and by the way, the message itself is not encrypted unless I also choose to encrypt it. So the message is plainly readable, and then we run that message through the same hash function that we ran through up here. So if we use, say, a SHA-1 hash up here, then we would use a SHA-1 hash down here, and that's just a formula or a mathematical calculation, one of the versions that you can use. So we run it through the same math, and we should get the same result right here when we get to this message digest portion. Okay, so we get this message digest. The next thing though is this still doesn't really confirm anything. This just confirms that I can run a SHA-1 hash against this message. What I need to do is to confirm that it came from this person up here. So on the recipient's end, they will receive this digital signature and the message. They get both parts of this, the message and the digital signature. These are two parts. Very often the digital signature here could be an attachment if it's an email message, for example, or if it's a set of drivers, it'll be an accompanying file with the mathematical result over here that is the digital signature. So here I've got my email message, I've got the digital signature possibly as an attachment, and then what we'll do is we'll take the signer's public key. Notice the private key was used here. We'll take the signer's public key. Now the public key and the private key are uniquely matched. The public key can only be attached to a single private key. If somebody else had signed this message, then this signer's public key would not work. So the signer's public key then runs against this signature function here and decrypts that original digital signature. When we decrypt it, we should then come up with this message digest, which should be identical to the message digest we came up with on our own using a SHA-1 hash. Then, if the messages match, we can confirm that indeed they did come from the original signer that they claim to have come from. Now, whether we're signing files, drivers, whatever, any kind of signing that takes place goes on in much the same process that we've seen here, as, for example, this email that I've talked to you about. By the way, I don't think this is specifically on the exam, but I just want to point out that if your email program on both the sender's side and the receiver's side does support this, then it's best if you can use SMIME. Okay? That's going to give you the most secure method. What happens when you send it using SMIME is it combines the original message and the digital signature into a single binary attachment. Okay, and this would be known as opaque signed. I'll put opaque here. Hopefully I can spell opaque. Okay, there we go. Opaque signed. On the other hand, if maybe you can support SMIME, but the recipient down here, well, they have an older email program and it doesn't support SMIME. So now what are you going to do? Because if they don't support SMIME, then they will have an unreadable message. So what you could have to do then is this could be then signed as a clear signed. Clear. That's supposed to be an L. Clear signed. And when this takes place, the actual signature is going to be appended to the bottom of the message. And that's just an FYI so that you know about the differences between those two. If you have any trouble sending signed messages to someone else and they keep saying, hey, I can't read this thing. Also, when you do send a signed message, then your certificate will accompany the message with your public key. Okay, even though it says private key here, don't let that throw you. It will send them your public key. They have to have the public key, your public key, in order to be able to perform this process that we see down through here. They do not receive your private key. I also want to make something clear as well when it comes to how the certificates are used with encryption and signing. When you encrypt something, you will encrypt with the public key. That encrypted file that you saw me encrypt a little while ago, that was encrypted with my certificate's public key. When I then double-clicked on it to open it, it decrypted it with my private key. If someone else were to try to open up that same file, and they double-clicked on it, they would try to decrypt it with their own private key, which would then, of course, not work. And we saw that happen. When we sign something, we sign it with our private key. Okay, this is the opposite. When we sign it with the private key, then we decrypt or read it with the public key. Okay, so just kind of bear that in mind. It's kind of a fundamental teaching of how signing and encryption takes place. Now, as you continue to plan out your PKI, you'll have to determine what kind of templates you need, and there are three basic versions. The first one that came out with Windows 2000 are version 1 templates, and these are static and you can't modify them. You have to use them pretty much the way they are out of the box. But some customers had customized purposes that they wanted to use their certificates for. So, starting with Windows Server 2003, Microsoft issued version 2 certificate templates. And by the way, templates are the basis of your certificates that are issued. So if you created a certificate template that said it's supposed to be used for code signing, then that's what it would be used for. Or if you wanted one that was used for encrypting file system, that's what it would be used for. Or you might want to customize one, saying, I want one that is used for smart cards and for encryption. Well, then you could customize one if you wanted to do those two functions. And that's why you might want one of these version 2, so you could customize that duplicate. Now, with Windows Server 2008, we now also have version 3 certificate templates that are able to also be customized as duplicates, and it also adds cryptography next generation, which is an extremely high level of encryption. It's a little bit overkill in my opinion, but it's kind of cool to have. However, you can only use that if you have Windows Vista or Windows Server 2008 operating systems, because the other older operating systems cannot read version 3 templates. You also have to determine who or what needs a certificate. Do my users need certificates? If they do, it's very likely that they'll need them for something like signing and encrypting email or encrypting documents, or maybe it's for smart card enrollments. Okay, that sort of thing. Do my computers need certificates? This is very likely the case if I'm going to use something like a virtual private network that needs to confirm the identity of the computer that I'm logging on with, or more likely IPsec, which also confirms both computers in the endpoint of that connection. So my computers might need to validate their identity with a certificate. I also need to decide if I want to issue certificates from a certificate authority, do I want to do this with manual enrollment or auto enrollment? A manual enrollment is generally going to be the case for something that's more sensitive. For example, you'll see after a while that we'll have something called a root CA. That's pretty much the highest point of my hierarchy. Well, it's going to be issuing certificates probably to intermediate or policy CAs or certificate authorities. And these are pretty high-level certificate authorities as well, and security sensitive. So I might want them to be manually issued, because I wouldn't want somebody to figure out a way to get an auto-enrolled certificate and to set up their own certificate authority in my network that could potentially issue false certificates of some type. So sometimes you want to do that manually if you really want to keep your thumb on those certificates that are issued. This is also the case if you don't have a whole awful lot of certificates to issue. If you got a dozen or 2 dozen certificates to issue, sure, I could probably live with manual issuance. But if I'm trying to issue certificates for a corporation of 80,000 users, I'm not going to do that manually. Okay, I'll do that till the day I retire. So then in that case, you probably want to use auto-enrollment, which is ideal for large issuance of certificates, and typically that's going to be used for your issuing CA, which is normally going to be the bottom tier of a CA or a PKI hierarchy. This is going to usually automatically enroll users and computers with their certificates, but it's not going to usually be used to enroll highly security-sensitive functions. Such as smart card enrollment agents, for example. That would be another one that I would probably opt to go with a manual enrollment instead, because that kind of an issuance would go to somebody of high-level security clearance and high sensitivity in our organization. Again, I wouldn't want people to be able to, even accidentally somehow, through an oversight in administration or something, to automatically enroll smart card enrollment certificates. Okay. Now, also, you need to determine if you have network devices that need a certificate. And this is something that works with something called NDES, okay, or Network Device Enrollment Service. And this is Microsoft's implementation of the Simple Certificate Enrollment Protocol, or SCEP. Okay. We've had SCEP in previous versions of Windows, but you had to use a third-party product to be able to generate the certificates to issue to your network devices, whereas now it's built into Windows, and that uses, again, the Network Device Enrollment Service. What this allows us to do is issue certificates to network devices that have a low-level operating system, such as a router or a switch. And then once we issue a certificate to it, we can confirm that we are indeed sending messages through our own router or switch with that particular certificate, instead of to an imposter, for example, that's trying to reroute our traffic. Then we'll also have services that might need a certificate as well. If I've got a service that starts up and runs under the system account, then that will be a certificate that is stored in the machine store. And when you look at your certificate stores, and I'll go back to my little certificate console that I created. By the way, I did save that, so I don't have to rebuild it every time. Then we see our personal certificate store right here. These are all stores. You'll also have your computer will also have a certificate store, a machine personal certificate store, and I haven't issued any certificates yet to this computer account, but that's what I mean when I say you'll have a machine store. With the user, they will have their personal certificate stored in the console. At least you can view it in the console, but it's actually going to be stored in the user's profile and in memory while the user is logged on. When they log off, of course, it's cleared from memory. So all of these questions that we have to answer, as well as the questions on all the other whiteboards that I've already had up so far, go a long way towards determining the kind of PKI infrastructure that I need. Before I can build my PKI infrastructure, I have to know the answers to these questions so that I know, where I'm going and what I'm trying to build. And in my design for my PKI, I also have to know what my security requirements are. I have to know what kind of private key length that I want. In your certificate, generally speaking, the longer the key length, the more secure it is, but it takes time to calculate that key length because it's a complex mathematical function. And when we do this, it also has a direct correlation to our lifetime. So generally speaking, the longer the key, the longer the lifetime can be as well. You're going to have a hierarchy where you're going to have a root CA, and you may or may not have intermediate CAs down here as well. Okay, and then these intermediate CAs may have issuing CAs that they also work with as well. All right. Generally speaking, the higher you go in this hierarchy, the longer the key and the longer the lifetime. So it's going to be a long key. Let's say it's a 2048 key length, and it's got a lifetime of, let's say, 10 years. Okay, so that would be common in something like a root CA. For an issuing CA, what we'll do is we'll make that shorter. We'll make that probably 5 years, okay, and maybe half the key length as well, so 1024. And then for my issuing CAs, I might have a 512-bit key length, and it might be a 2-year certificate for those. So you can see again that the longer the key, the longer the lifetime, generally speaking. And then for the user certificates, the actual certificates that it actually issues to my users or my computers, their certificates are probably also going to be, well, 256 or 512. You know, that's still common nowadays, 512 length keys, but maybe 1 year for the expiration of the user certificates or the computer certificates that are in general use. Another thing to keep in mind is that we generally want to use as long of a key as we realistically can, but the longer keys are computationally more difficult, therefore they're harder on the processor. So if I'm trying to issue 80,000 certificates to my generic users and computers, I don't want to use a 2048-bit key length to all of them. It might take a couple of minutes for each one of those users to get a certificate, and if I were to do something like that, I'd probably put upon myself a denial of service attack. I'd create my own denial of service attack because my CAs would be so busy performing the calculations they would not be able to practically distribute those certificates to my users and computers. So you have to be realistic as well in terms of the issuance. Also, some applications and devices might not support long keys, such as Cisco VPN 3000 devices, some of the older Java applications. What else? Nortel Contivity devices. Some of those kinds of things won't support the longer keys. You just have to know in advance. So check that out. Also, generally speaking, the more sensitive the account, the stronger the algorithm. So, for example, up here at the root CA, which is this most sensitive certificate authority that I have, I want to give it a longer key length that we talked about earlier, but I can also afford an inverse relationship with the longer expiration of it. And I'll probably want to give it a stronger mathematical algorithm. There's all different kinds of mathematical methods that can be used to calculate this key. All right, so we'll generally make those stronger, and again, we'll make the stronger algorithms higher up in the hierarchy, and then when we come down here to the bottom where we're actually issuing certificates to users, those will probably be a little bit more lightweight, but still good, because we can't afford all the processing power of a strong algorithm for these generic kind of certificates. And I also explained to you just a moment ago the lifetime between the parent and child hierarchy. Again, you generally, as you go up the hierarchy, usually double things. So 2 years here, double that would be 4 years, but we have a 5-year from our drop-down list, so we'll choose 5 years. Double 5 years is 10 years. Likewise, we also usually double our key lengths, 5, 12, 10, 24, 20, 48. Then you also have to understand what kind of clients you have for your business and what kind of requirements they have, or what kind of job requirements your own people have. You might have a client that says, maybe it's a government job, and they might say we need to have FIPS 140, FIPS 140 standard for our encrypted or signed data. And FIPS would be the Federal Information Processing Standard, and right now it's at version 140-2. It's extremely complex standard, but it might be required by certain government contracts and the like. And then you also have to determine your own job requirements. Do we have programmers that sign things, sign code, or that sign drivers and things like that? Well, what are their requirements? What do they need to have for signing? I also have to take a look at my business requirements. One thing I really got to look at, especially these days, is you got to look at the cost of these things. I mean, you could come up on paper a really nice Visio diagram of dozens of certificate authorities, all for different purposes and all really highly maintained and with the latest hardware and look really good on paper. But when you calculate the bottom line for your boss, they may tell you that you need to go look for a new job because it's so stinking expensive. So you may need to really whittle that down, and there's a number of ways you could potentially do that, but it's all kind of related to the size of your organization and the number of CAs that you feel you absolutely have to have, how dispersed your company is. If you're in one building, for example, then you're going to be able to afford a lot fewer CAs more than likely. But if you're a global organization with hundreds of different sites, and each one of the sites is going to need to have their own issuing CAs, then you're going to have a proportionately more expensive distribution of certificate authorities throughout your organization, because that's going to have one for connectivity and availability purposes in all those different locations. Another thing there would relate to the purposes of the certificate authority. Are you just using this for code signing, or do you also need to have computer certificates so that you can validate the systems on IPsec? Or do you need user certificates for EFS? If that's the case, you might have one certificate authority for machine certificates, for example. You might have another one for user certificates that are doing EFS. Also, the number of tiers that you have. In the previous diagram I showed you, we had a 3-tier architecture, and we'll look at that again. We're going to revisit that and go into some more detail with that. But you could potentially eliminate the middle layer if you had to. If you absolutely had to cut corners, you might be able to eliminate the middle layer in some organizations. So you'd have a root CA, and that would be issuing certificates directly to your issuing CAs, which then in turn issue certificates to users and computers. So that would be a 2-tiered architecture. Then you might also be able to consider an external CA. If you don't really need a whole lot of certificates, if I'm not issuing certificates to 80,000 users, I'm only issuing certificates to a dozen programmers that I have on site, and maybe I need a certificate for my web server. So I only need a dozen or so certificates. I'll probably just get those from an external certificate authority. Thought, VeriSign, one of those types of companies. And if I do that, then I'm really only paying for the certificates, whatever they charge for their certificates. I'm not really paying for any hardware in particular. And there's also some possibilities where you're going to mix and match this. So, for example, for my web servers that are on my DMZ or my hosting service, I probably have them using certificates that are from a public external CA, like VeriSign. That way, when people make a connection to those servers, they already have the VeriSign trusted roots in their local store, so they don't have to go through any hoops to be able to work with my website. On the other hand, if I were to issue a private certificate to that, a privately issued certificate to that web server, then people would get an error message in Internet Explorer, and it would give them a warning saying you might not be able to trust my website. Well, that would be kind of embarrassing, so we wouldn't want to do that. So I'd probably use an external CA for my web servers, and I might use an internal CA with all the associated costs and everything else that I've gone over for my internal users and computers. Then I also need to make sure that I have high availability of my issuing CAs. That's why I was talking to you earlier about this dispersion. If I've got hundreds of different sites out there, then each one of those sites needs to have availability for an issuing CA. That's why I might have to have an issuing CA in each one of those sites. Or if I've got larger branch offices, maybe I can at least put one CA in my branch office for the East Coast, and then in a hub and spoke kind of a topology, have my smaller branch offices talk to my bigger branch office where there is an issuing CA that they can communicate with. So just a number of different strategies and things to think about with the availability. And then there's the liability. If I come up with my own PKI and I have business partners or third parties or customers use my certificates, and then my certificates somehow get compromised, I could be liable for secrets that my customers or somebody else is guarding with the certificates that we've been using. So there is a liability thing to consider there, and you just have to be aware of it. Also, if I have external partners, maybe I've got another company that we do quite a bit of business with, or maybe that we're part owners with, or something like that, where we have a long-standing relationship, then we might want to use one another's private certificates to both sign, encrypt, whatever it is that we need to do. And so for that sort of thing, something like qualified subordination might need to come into play. And with this, you would take your own PKI hierarchy, and you would be able to feather in, so to speak, the other company's CA, and logically speaking, it would kind of become like a child CA of your own PKI infrastructure. And then finally, you have to take a look at your own Active Directory. In almost any of the contexts that we're talking about, and certainly for exam purposes, almost always we're going to consider Active Directory in the mix. This is really only going to be relevant for enterprise certificate authorities, because enterprise CAs can interoperate with Active Directory and leverage Active Directory to do things such as store copies of the certificates that I issue to my users. That way, I've always got kind of a running backup of my users' certificates. Also, I have to take a look at how many forests I have. Enterprise CAs can be associated with only one forest. So if I have two forests, I might have to build twice the PKI infrastructure, one for one forest and another one for the other forest. Also with my domains, it really goes to how we administer our domains. If we're really centralized, then maybe I've got a parent domain or a root domain, and I can do everything from there and then issue all of my certificates throughout all of the children. On the other hand, if we're decentralized and all my child domains have pretty well their own IT staff and a high level of autonomy, such as that you might find in a lot of university organizations, for example, then they will probably have to create their own PKI infrastructure in each one of those other domains. So that would be a very decentralized, but also potentially costly method for doing that. And then, if I want to take advantage of all the 2008 capabilities, then I would need to update my schema to Windows Server 2008 version of the schema. And remember, the schema is kind of the skeleton for Active Directory, and it defines all of the objects and attributes in Active Directory. We have to update that to the 2008 version if we want to use 2008 certificate authorities. And just as a quick review, for if you're not quite familiar with that function within Active Directory, let me just go to a command prompt. If I wanted to update my Active Directory, you could do this even in a Windows 2000 domain. You can update the schema without actually having to upgrade your domain to Windows Server 2008. You just put in the Windows Server 2008 DVD into the tray, and then you would go ahead and run these commands: AD prep space domain prep, and you would also run AD prep space / forest prep. And once I'd done that, even if the rest of my domain was 2000 or 2003 or something like that, that was the operating system of my domain controllers, the schema would still be updated, and I could still use Windows Server 2008 certificate authorities. In this nugget, we took a look at designing a PKI, where we started off by taking a look at why we even need a PKI. What kind of purposes do we have? Do we want to work with IPsec? Do we want to encrypt documents? Do we want to sign or encrypt email? A lot of different things go into deciding why you even need a PKI, and once you decide what your needs are, that will drive how you design the rest of your PKI. We also took a look at a quick example of encryption, where I used a self-signed certificate, at least, to encrypt a document, and then we saw what happened when we lost that certificate, can no longer access the document. We also took a look at signing and how that works in an email example, and then we took a look at security templates, or rather certificate templates. With certificate templates, there's 3 different versions. Remember, for Windows Server 2008 version 3 certificate templates, you can only use those with Vista and 2008. Also, we took a look at who needs the certificates. If it's going to be thousands of users, then your PKI infrastructure will look dramatically larger than if you have only a handful of users. So we took a look at some of the needs that we have there, and including network devices. And then we took a look also at the security requirements that you might have. Generally speaking, the higher up the hierarchy you go, the more stringent your security requirements are, and the longer the key lengths, and the more difficult the algorithms, and so forth. Also, we took a look at the business requirements. Might have a contract with a company that requires certain kinds of processing standards and certificate standards. We also took a look at Active Directory, which mostly relates to an enterprise CA because it can directly integrate with Active Directory. Well, I hope that, I'm getting another text message from my wife. She probably got an email now asking for all of our social security numbers and bank account numbers. Well, I hope this has been informative for you, and I'd like to thank you for viewing.